Autonomous large language model agents face a strict operational contradiction. To be useful in a multi-agent system, they need to be highly responsive, running 24 hours a day, ready to execute tasks. But keeping them active means repeatedly invoking the LLM to check their status, and every single invocation incurs an API token cost. Current orchestration frameworks like CrewAI or LangGraph manage agent readiness through polling loops or cyclic graphs. They maintain liveness by constantly asking the language model if there is new work to execute. This equation illustrates the cost of that continuous polling approach. The daily token cost equals the number of agents deployed, multiplied by the seconds in a day, divided by the polling interval, multiplied by the cost per poll. If we deploy a modest fleet of 75 agents and set them to poll every 30 seconds to ensure they remain responsive, those variables fill in quickly. This resolves to 21.6 million tokens burned every single day. At standard API rates, that totals over $15,700 a year. That budget is spent solely on asking the LLM if it has anything to do. The expense exposes a flaw in multi-agent framework design. Relying on continuous polling means treating the LLM as the substrate for liveness itself, binding basic software uptime directly to expensive cognitive inference. The question, is the agent alive, is a simple binary state. It is a pure input-output query, and verifying it should never require an LLM call. The heart architecture is engineered to resolve this by explicitly decoupling the agent's liveness from its cognitive load. By separating these functions, the system drops the token cost of keepalive signals to zero. Solving the multi-agent scaling problem requires abandoning pure compute-heavy paradigms. System architecture must strictly separate the intelligence of the model from the basic operational state of the software. The first pillar is the pulse chamber. Operating as a pure I/O loop, it uses an MQTT stream to broadcast status. No LLM node is here. To maintain its heartbeat, the agent simply publishes a keepalive message every 10 seconds. An external monitoring tool, the MISBA dashboard, subscribes to these topics. It interprets these data pings to track the fleet. If it logs exactly 3 consecutive missed pings, a 30-second window, the agent is marked offline. Shifting liveness to this isolated data stream achieves complete failure domain separation. If the external LLM provider experiences a total outage, the agent's local infrastructure remains online and reports its active status accurately. True system resilience at scale relies on this exact isolation. An agent's ability to exist online must operate independently of its intelligence provider. The second component is where cognitive tasks are budgeted and executed, the schedule chamber. It dictates periodic LLM invocations based on an agent's configuration file, setting the wake-up interval, the prompt to run, and a daily cap. The primary operational danger in any scheduled system is the unbounded timer. Without limits, a schedule can trigger infinite execution loops that quickly drain API budgets. To prevent infinite loops, Hart places a 64-bit daily atomic counter directly between the schedule chamber and the LLM. It acts as a rigid mathematical gatekeeper, resetting precisely at midnight. This chart tracks an early agent, Travel Rescue. Without a daily cap, it executed 288 wakeups daily. Applying the daily atomic counter and widening the interval dropped redundant compute by 83%, flatlining at the 48 wakeup cap. Enforcing this limit halts runaway loops at the infrastructure level. It neutralizes redundant calls without relying on the LLM to understand or manage its own rate limits. Any autonomous system that invokes an LLM on a timer without a hard deterministic cap is mathematically guaranteed to experience runaway costs. The final architectural component is the idle chamber. It manages bounded autonomous exploration, triggering only when the agent detects a prolonged period of user inactivity. When agents explore their environment, they often find nothing to do. If an agent records every unproductive wake-up in its memory, it suffers from context window pollution. These useless logs compound the token cost of every future interaction. To eradicate this memory pollution, Hart implements ghost mode, which is driven by a specific explicit command called the idle protocol. When the LLM wakes up, it evaluates its environment. If no action is needed, it outputs the string bracket IDLE bracket. This triggers an immediate state rollback, deleting the initial prompt and the idle response. The interaction leaves zero memory footprint. In a multi-agent environment, waking up and verifying that no action is required is highly valuable information. It is a successful operational check, not a failed invocation. Managing the LLM state through explicit rollback removes the friction of wasted polling. It transforms unproductive wakeups into zero memory, near zero cost efficiencies. Even with strict architectural boundaries, production software encounters errors. Pathological retry loops and external tool timeouts will inevitably occur. Heart isolates these failure modes using a dual trigger circuit breaker. It sits directly between the three chambers and the LLM, tracking language model failures on one switch and external tool call failures on the other. Consider a stock price agent that encountered an external API error while attempting to fetch market data. That single failing external tool caused the agent to enter a retry loop. It burned through its entire daily atomic counter in under an hour, prompting the developers to add a specific per-wakeup tool cap. When either switch on the circuit breaker trips, the system alters its behavior. The schedule and idle chambers silently skip their subsequent wakeups to protect the system's budget. Because the architecture is fully decoupled, the circuit breaker can completely sever the LLM connection, and the pulse chamber will continue its MQTT broadcast. The agent remains online and visible on the dashboard, even while its cognitive functions are safely paused. Achieving determinism in autonomous AI does not require perfect execution from the LLM. It requires rigid infrastructure failsafes that gracefully catch and isolate non-deterministic errors. This is the complete heart architecture in motion. The three chambers run concurrently, independent of one another. The division of labor is exact. Pulse handles liveness, schedule manages intelligence, and idle controls exploration. In production, the local kin team deployed this architecture across 75 agents. Over 1 year, they generated 315 million heartbeats, maintaining 99.2% system uptime. By severing liveness from inference, that massive scale of continuous agent presence was achieved without spending a single cent on keepalive token costs. As multi-agent deployments expand, continuous presence becomes a core operational requirement. Providing that presence is a problem of software architecture, not prompt engineering. Ultimately, to build truly scalable and resilient autonomous systems, the key insight is simple. An agent's heartbeat must never require a brain.